We'll be looking at how to apply the stiffness method to continuous beams. The objective for today is to apply the stiffness method to beams with NOK greater than 1. What we're going to learn through an example. Since NOK is greater than 1, we'll be looking at a matrix formulation of the stiffness method. We'll see how we determine degrees of freedom and draw the deformed shapes. We'll be using appendices C and D to determine member forces from the DOFs as well as from member loads. And in a subsequent video, we'll be seeing two different methods of force recovery. We'll be working through an example today. So let's look at the problem statement. We have a two-span continuous beam that's subject to a uniform load of 2 kibs per feet. The span lengths are each 20 feet, and I've indicated in the blue arrows the 3 degrees of freedom. Now you might want to go and calculate NOK and determine that indeed there are 3 degrees of freedom. In this problem, we'll use a member stiffness EI. We'll be using the terminology L for length. And our ultimate goal in this video and the next one is to find member forces and reactions. Now this problem we've previously solved with the flexibility method. So if you go back to that problem, you'll be able to see the same problem being solved in a different way. Our first step in this method is to draw each of the degrees of freedom and determine the forces that must be acting at the end of the members to enforce that deformed shape. What I'm showing here is degree of freedom 1. Now recall that when we displace a degree of freedom, we hold all of the nodes unmoved except for the one that corresponds to the degree of freedom. So degree of freedom 1 has to do with the rotation of the left node, which is why we're showing this node rotated. The other nodes stay in the original position that they were in. Once I determine the motion of all the nodes, I can come in and determine the deformed shape for the left side and for the right side. My next step will be to draw the member forces that must be present to hold that shape. These are the forces that must be present. Let me walk you through why that is. Now first of all, a note. Obviously this isn't an equilibrium. I'm not showing any of the shear forces. The reason is that there's no translational degrees of freedom, so these aren't going to enter into the problem. We'll see the shear forces in the force recovery at the very end. The way that I determine these member forces, first, I look at the deformed shape of the member. I look at what the curvature is locally at the end. So at this left end, the curvature is negative. At this right end, the curvature is positive. I then think about what moments must be present at those ends to cause that curvature. These are the moments that must be present at the left end. These are the moments that must be present at the right end. And so you can see the correspondence between now the moment right here and the moment that I've drawn on the member, and on the right side, the moment that I've drawn on the member. Given these, I can now draw equal and opposite moments on the node. On the right side member, there's no deformation, so there are no forces. It takes no force to keep the member undeformed. Now, what are the values of these forces? Well, here's where we use Appendix D. If I look up Appendix D, this is the figure that I see. Now, the shape doesn't correspond exactly to the deformed shape that I've drawn. What's important to recognize is which is the end that has the unit rotation and which is the end that remains unrotated. So this term F1 corresponds to the end that has the unit rotation. This term F2 corresponds to the far end. That's why on this side, M1 is going to correspond to the 4EI over L, and M2, which is the far end, is going to correspond to the 2EI over L. Let's move on to DOF2. I should have mentioned last time, but I'll mention here, that degree of freedom 2 is drawn for a unit displacement. Now, of course, it's not going to displace a unit amount, it's going to displace a different amount, and so we'll find that scaling factor through this process. Shown here is the displacement for degree of freedom 2. Once again, let's walk through how this came to be. We rotate the node having to do with the degree of freedom. We keep all the other nodes in the same position that they originally were in, and then we sketch the deformed shape that preserves the same displacements and slopes. So on the right side member and on the left side member, we have the shapes shown here. The next step is once again to show the member forces that must be present to hold those shapes. Again, We're not showing shears because we don't have any displacement degrees of freedom. We'll walk through once more the procedure that we use to think about the directions of the moments. Shown here are the deformed shapes. To enforce these deformed shapes, we need the moments that are shown here, which are the same moments that are applied to the free body diagrams below. Each of these moments is going to react equal and opposite onto the joint. So for instance, at the very left end, this M2 is the force on the member, equal and opposite reaction onto the joint. On the left end of the right hand member, the moment on the member reacts equal and opposite onto the joint. For the values of these, we use the same drawing from Appendix D. We actually already calculated these quantities. We calculated the value F1 that corresponds to the side that the unit rotation is applied as 4EI over L. F2 that corresponds to the side away from where the unit displacement is applied, we calculated as 2EI over L. These are already identified in the figure, and we've already found these quantities. For degree of freedom 3, once more we draw DOF 3 for a unit displacement that's going to be scaled later. I'll go a little bit quicker this time. Once again, we're not drawing shears since there are no displacement degrees of freedom. The explanation will be exactly the same for why we draw the moments the way that we draw them. We'll use the same entry from Appendix D. We've already calculated M1 and M2. We write down the values here. So you can see that this procedure can get very repetitive. That's a good thing. We're doing the same task over and over, and once you get good at this, it'll become very quick. Last consideration has to do with the member loading. This is the member loading right here, the 2 kips per foot that act on the member itself. As you recall from last time, the way that we deal with the member loading is that we see what forces are necessary to hold the nodes fixed at the same time that we apply the load. These are the member forces. Once again, I'm not drawing the shear forces because we don't have any displacement degrees of freedom. You can come up with these in 2 ways. You can think your way through it, or we can get them from Appendix C, which is the approach I'll take here. Now you'll notice that there's a few differences between what I've drawn and what's shown in Appendix C. Specifically, the direction of F2 here is different than what I've drawn. Why is that? Appendix C is shown with all of the forces in the positive sign convention. And so you can see that the value of F1 is equal to the negative value of F2, an absolute value of both QL over 2. What this negative sign on F2 says is that F2 actually acts in the opposite direction. We notice the value here that I've indicated as M3 at all these locations is equal to the QL squared over 12. I'm using W instead of Q, and so we write down M3 is equal to WL squared over 12. Given that W is 2 kips per foot, L is 20 feet, we can calculate the value of M3. These are all the preliminary steps that are necessary to set up the stiffness method. We'll take a pause here, and then we'll resume in a subsequent video to see how we assemble all this information and solve for the unknown rotations at the degrees of freedom 1, 2, and 3.